So here we go. We have a pulley and two objects. Let's say the masses of the objects are equal. If you let go, they're just going to sit there without motion if the masses are equal. However, if we make one object bigger or heavier, and to mess with your mind, I'm going to make it smaller. Let's say this one is gold and that one is aluminum. Gold would weigh more even if it's smaller, right? Remember density. So if we have a system of two objects, and when you have a system of two objects, they're going to be moving as one if they're connected by a massless unstretchable string, as we have here. So we have a pulley right here, which is affixed, and then it's rotating without friction, and the string, since this one is heavier, is going to start rolling this way, and then this part will be rolling upwards. So when we are analyzing this, we're going to look at our objects separately from each other, free body diagram separately. So the 20 kilogram object will have force of gravity that outpowers force of tension. How do we know that? Well, because when we let go, the system is going to be accelerating downwards. And you will see the acceleration in our lab for Atwood machine. So mg and tension. This is for my 20 kilogram object. Now I'm going to repeat that for my 10 kilogram object. But for 10 kilogram object, I will keep, watch me, I keep the same force of tension here. It's still two boxes because, like I told you already, force of tension is uniform throughout the string. To make it easy, I'm going to just use this one box right here. So then this is my mg. And to distinguish between the two m's, I'm going to say this is m1 and this is m2. So then look at my Newton's second law for the first one. For the first one, I had mass times acceleration, mass 1 times acceleration. We have gravity minus tension. And again, to distinguish between the two objects, I'm going to use the formula for gravity. It's going to be m1g minus tension. Then I'm going to grab my second object, which is m2, acceleration equals, and see how tension is greater here. Tension for the object that is going to be accelerating upwards, tension is greater than mg. So I'm going to say as much. Now notice that this is a system of equations. Mathematically, when I have a system of equations, I can do whatever I want with the two of them. I can substitute, I can eliminate, I can multiply them by each other, I can add them to each other. So here, I'm going to add them. The reason why I'm doing that is because I notice that I have positive tension and negative tension, and they are the same force. So if it is tension and negative tension, when I add them, they cancel each other out. Then acceleration is the same acceleration because, like I said, they're connected with the same unstretchable string, so they will be accelerating at the same rate. So I can say acceleration, and I will factor the masses out, m1 plus m2. Both of them are accelerating with that a. And then what do I have? I have m1g from the top minus m2g from the bottom. So ultimately, this is like acceleration times the sum of mass equals g times the difference of masses, the heavier minus the lighter. And then I can say that my acceleration for the whole system is going to be m1 minus m2 over m1 plus m2 times g. So let me calculate that real quick. 3.3 meters per second squared. Now, if I know my acceleration, I can go ahead and figure out force of tension in the string. And because of my rounding, if I keep it at 3.27, or better yet at 3.2667, for example, I can get force of tension from either of the equations. You will see that if I choose one for the top one, then I'm going to have 20 times 3.3 equals 20 times 9.8 minus tension, from where tension is going to be 20 times 9.8 minus 3.3, 130 newtons. Then if I take this one, then I'm going to have 10 times 3.3 equals tension minus 10 times 9.8, from where tension is going to be 10 times 3.3 plus 9.8. Technically, it is 131 newtons. So it looks like it's different, but if you use not 3.3, but up to 5 sig figs, your forces are going to be closer in their value. So you are welcome to use either one of the equations. Your results for tension are going to be very, very close. So it doesn't really matter which one you choose. So then in class, what we did, we practiced with a different set of masses. So you're welcome to continue that. Steps are going to be the same. We used a new configuration. We used one of the weights was on the surface, and the surface was frictionless. And we had a string that connected our object on the surface to an object that was hanging. So this is the setting for your lab. So the object that is on the surface obviously has gravity and normal that are going to be equal to each other, and therefore balance our object out. I don't know, are they equal-ish? Not very good because it should be along the string, but I'm just showing the forces, so forgive me for that. And then I'm going to look at my hanging object. Hanging object will have the force of tension that is equal to the force of tension that I already drew. So it's about 3 boxes, so here. And then downward force, which is force of gravity. I'm going to draw it longer. So this is my M1G. So now, again, just like before, we're going to write down Newton's second law for each one of them separately. Newton's second law tells us that if we have a non-zero net force, then then our object will accelerate. And I'm going to look at my objects separately. So I have tension equals M1 times acceleration. That is it. Why am I not looking at normal and gravity? Well, because they're not along the surface and they balance each other out. They do not participate in creating the net force. The only unbalanced force for my object on the table is force of tension. Then I'm going to look at my hanging object, which is right here. For the hanging object, I have minus tension equals mass times acceleration. I can take my tension and my negative tension and cancel them by adding these two equations together. M2G equals acceleration times M1 plus M2. Therefore, acceleration is going to be just force of gravity on the hanging object divided by the sum of masses, the hanging and the mass on the table. So therefore, acceleration will be, let's say that this is 30 kilograms, and that is only 5. So then I will have 5 times 9.8 over 1.4 meters per second squared. And then I can go back and figure out my forces of tension. The first equation would be the easiest because the first equation tells me that tension equals mass 1 times acceleration. It's the one that is sitting on the table. 30 times 1.4, which is 52 newtons. For the equation and go for 5 times 9.8 minus tension equals 5 times 1.4. They should be equal. So 5 times 9.8 is 49, minus tension equals, this is 7. Therefore, tension is going to be 49 minus 7. Look at that, 42. Why did I write 52 here? This is 42. Boom, boom. 42 newtons and 42 newtons, the same force of tension. That was for the setting where we had absolutely no friction or negligible friction. CP, you're free to go. I'm going to add a little bit of kinetic friction. I'm going to say that my mu kinetic is 0.2, for example. What will change? What will change is that force of friction is now going to be opposing force of tension. Therefore, M1 times acceleration will be tension minus mu m1g. Because remember, force of friction is mu times normal force, and when it's flat on the surface like that, then it's just mu times mg. And then the hanging object is mass 2 times acceleration. Actually, which one was 2? Which one was 1? Let's say this is 1 now, and this is 2. Equals m2g minus tension. System of equations, add them, gets me acceleration, sum of masses, equals, tension cancels, m2g minus mu m1g. So I can say that my acceleration now is g times m2 minus mu m1, all that divided by the sum of masses, m1 plus m2. So acceleration will be 9.8 times the hanging mass, which is 5, minus 0.2 times 30, which tells me in a system like that with friction, this needs to be heavier. I'm going to make it 10 kilograms then. All right, then I'm going to have 10 minus, and now I have 40 meters per second squared is my acceleration now. Just to make sure that you see the difference between friction and no friction, I'm going to quickly, this will disappear, I'm going to quickly recalculate. If we had no friction, just one mass, which was 10 times 9.8 over 40. So 9.8 over 4 meters per second squared. So 2.4 meters per second squared if we had a heavier mass, which is 10 right here. This is the force of tension, 88.2 newtons. This is with force of friction. Now, without force of friction, what do you think? Will it be greater or less? Let's see. It's going to be 132 newtons. So that's how you find acceleration with or without force of friction on this contraption. And then the final part, which you will be doing on your own after the lab, you will have an object that is on an incline. Now, let me adjust the incline a little bit. And that object on an incline will be connected to another object that will be hanging off. And you're going to be asked to find a bunch of things for this system. And again, you're going to think about these two objects separately for Newton's second law and then write everything out.